Dear civil engineering students and faculty members and other viewers, um, welcome to Next Generation Structural Analysis Laboratory of Galgotias University. We will be deriving the vertical and horizontal deflection of the curved bar. Now this is the curved bar as shown in the figure, and it is subjected only to vertical load W. And because of this vertical load, we are getting two things. One is vertical deflection. Another one is horizontal deflection. This is a curved bar which is said to be a quadrant circle, and the radius of the bar is R. So once you know the radius of the bar and once you know the loading and also the flexural rigidity EI, you will be able to determine the del V and del H. Let's see how to do that. And this time we will be employing two methods. One is strain energy method. The second one is Castigliano's theorem. Using these two methodologies, we will be deriving del V and del H. Let's go inside. So this is where we go. This is the equipment supplied by equipment from England, and the student will be performing the experiment here using this curved bar, and he will apply the loading here, which is the W, and the student will measure the horizontal deflection and vertical deflection. So this will be calculated by the VDOS software, which is connected to the machine by the computer. And once the student calculates the vertical deflection and horizontal deflection by using VDOS software in the computer and performing the experiment using this machine, then finally he can verify the computations using manual calculations. So let's derive the manual calculations. So here we go. As I told you earlier, only a vertical load W is applied, and because of this W, there will be del V and del H. So this is what we are going to derive. And note on that we should know what is the value of W, and we should know what is the value of the radius, and also we should know what is the flexural rigidity EI. So once you know that you can determine del V and del H. That is the beauty of civil engineering. And proceeding further, so this is the diagram. In this diagram, you can see that this is theta, and this angle is 90 minus theta. So this is hypotenuse. So from the basic trigonometry, you can find out the lever arm distance. So what's the lever arm distance? The perpendicular distance between the point of application of the vertical load and any arbitrary point X. So this distance is said to be the lever arm distance. So from this lever arm distance, we calculate that R cos 90 minus theta degrees is the lever arm distance, which could be simplified further as R sin theta. So if you want to find out the horizontal component, here you have the horizontal component, vertical component, that is R sin 90 minus theta. Proceeding further, we will use strain energy. So strain energy stored in the structure is U equal to m square ds by 2 EI, where ds is nothing but any small infinite seminal length d. So this length is said to be ds. Here we are calculating the lever arm distance, that is R cos 90 minus theta, which is equal to R sin theta. That has been calculated as the lever arm distance. So this is the distance between the point load and the any arbitrary point X in the bar. So here we go. First of all, we should find out what is this length ds. This ds is the arc length. So from the basic trigonometry, we come to know that r multiplied by d theta is the ds. Substitute this value in the expression for strain energy. You get m square r d theta by 2 EI. Now, so once we end up with the expression for strain energy stored, now we write down the expression for bending moment at any point X. So that value is nothing but W times R into cos 90 minus theta, which is equal to W into R sin theta. So this is the expression for bending moment. Now you substitute the value here in the expression m square ds by 2 EI. So then on evaluation of the integral, finally we end up with this calculation. So this is the final expression, W square R cube into pi by 2 EI into 4. Once you calculate that, then you can see that is the strain energy expression. So proceeding further, if you want to calculate the vertical deflection, the Castigliano's first theorem says that if you apply a point load at any structure, the partial derivative of the partial differentiation of the strain energy with respect to the particular point load is equal to the deflection. So that is the Castigliano's first theorem. So once you apply Castigliano's first theorem and simplify this W square R cube pi by 2EA into 4, that's the strain energy, you will be ending up with the vertical deflection. So we have calculated the vertical deflection. The next step would be to calculate the horizontal deflection. Note on that in this structure we have applied only vertical load. We do not apply any horizontal load. So you can see that here WV is the real load and this WH is a dummy load. So why do we apply this dummy load? WH is that we want to know what is the horizontal deflection. So once you obtain the strain energy stored due to these two loads, finally you substitute the value of WH is equal to 0. So this will help you to evaluate the strain energy stored, and once you differentiate that with respect to WH, you will be ending up with the deflection, that is a horizontal deflection. Yeah, and before proceeding further, we should know what is the lever arm distance between the vertical load and the arbitrary point X. So you can find out that the vertical load W is at a distance R sine theta from the arbitrary point X, and also you can see that this horizontal load is at this horizontal load has a lever arm distance of R minus R cos theta, because we know that this is R cos theta and this distance is nothing but this is R. So on further simplification, we find out this distance is the lever arm distance for WH. So that is nothing but R times 1 minus cos theta. So we have two lever arm distances. One is for the vertical load, which is nothing but R sine theta, and for the horizontal load, we find out that the distance between the point X and the point of application of the load is R into 1 minus cos theta. So once we know the perpendicular distances between the two loads, that is WB and WH, we write down the expression for moment. So this is the expression for moment carrying two loads, WV as well as WH. Proceeding further, you substitute in this expression for finding out the strain energy. Now, up to this, most of the people will understand. So after this, what the students do is they will expand this expression in the bracket. That is, they will expand this WV R sin theta minus WH R into 1 minus cos theta whole square. But that is not at all required, because you can apply the second step, that is the Castigliano's theorem. So once you have the strain energy, you apply the Castigliano's theorem. So here you have to find out the horizontal deflection. So you apply dou U by dou WH. So you can differentiate this expression with respect to WH. So you have after differentiation you end up with this equation. So in this equation it is further simplified here and shown here. So this is minus 0 to pi by 2 R times WB R sin theta into R into 1 minus cos theta d theta by EI. Yeah, this is what we have to integrate. So that is the same expression has been given here. And proceeding further, you can see that here the del H is equal to dou U by dou WH. You have this expression. And finally, after simplification of this integration, we have minus WR cube by 2A. So this is how we calculate the horizontal deflection. So here we have employed two methods. One is the strain energy method and another one is the Castigliano's theorem. So using that we have calculated del H as well as we have calculated del V. Note on that we have applied only one load, that is W, vertical load is applied, and using for this vertical load we want to find out the del V and del H. Now you can imagine that the del V is in correct direction and the sign is positive here. But if you take the expression for del H, it means that del H happens in the opposite direction, so that no need to worry about the sign, because minus indicates that our assumption is wrong, and it's not wrong, but the assumption says that the load was applied in this direction. Okay, but according to this minus, actually we should have applied the load in this direction. If you have applied the load in this direction, for sure you will get here the positive sign. So since we have applied in the opposite direction, we have got negative sign. But the point is, we want to know only the magnitude of deflection. So if you compare the magnitude, we do not require the sign, we require only the magnitude. This is how we solve the curved bar using strain energy method and Castigliano's theorem, and end up with horizontal deflection and vertical deflection. Thanks a lot for watching. If you have any doubts, you mention in the comment section.